class, that's all for today. Thank you. Wait. Before you go, I want you to search on what is entropy, how to calculate it, and its practical application. So, bye guys.
Hi, Dad!
Oh, you're here. Could you get me a glass of water, please? With ice.
Yes, Dad.
Sorry.
Here, Dad.
Oh, thank you.
Oh, Dad, I have a question
What is it?
about my assignment. So, it is about entropy. So, you know what's entropy?
Of course, my dear. Entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion to mechanical work, often interpreted as the degree of disorder or randomness in the system. The best example of this is the melting of ice in this water. Did you see it? See that?
Really?
It's melting. It's an example of entropy. So if you want to learn more about entropy, just follow me.
It does the.
What we want to do in this video is start exploring entropy. When you first get exposed in the idea of entropy, it seems a little bit mysterious. So in this video, we hope to give you a very strong intuition of what it is. So, one of the more typical definitions, or a lot of the definitions you'll see on the entropy, they will involve the word disorder. So it might be considered as a disorder of the system.
So now with just that definition in your hand, I want you to compare this system to this system and ask yourself which of these has more entropy. So when you look at these rooms, you might say, okay, this room here looks ordered. It's a clean room, and this over here looks disordered. It's a messy room. So if all of you had this definition, you'd say, okay, maybe this one is more disordered or has more entropy. But this isn't exactly the case. This form of disorder is not the same thing as this form of disorder. So something being messy does not equal to entropy. Entropy, this kind of disorder, is more of the number of states that the system can take on. So what do I mean by states of the system? If I have a container, and if I have 4 molecules that are bouncing around, well, this would be a particular state, a particular configuration. But the system, these molecules are bouncing around could take on other configurations. Maybe the yellow molecule is over here, the blue molecule to get over here. Maybe the pink molecule is now over here, and now the green molecule is over here.
And so, a system can take on a bunch of different states, but there could be many more states for this system. So each of these are a particular state for the system. So imagine this system where I have this box with 4 molecules in it. And let's compare it to another system, to a larger system. For example, a larger box. Let's say it has 2 yellow molecules, a blue molecule, a green molecule, a magenta molecule, and mauve molecule. So this system that is larger, there's more places for the molecules to be, and there's actually more molecules in it. This can actually take on more configurations or more states compared to the small container earlier with 4 molecules, hence having more entropy. So when we talk about disorder, we're really talking about the number of states something could have. And it makes sense that this thing, you could imagine that there's a lot of stuff moving around in a lot more different directions, and they have a lot more space to move around. So it makes sense that the system as a whole has more entropy. So when we talk about entropy, we're not talking about any one of the particular states. Any one of the particular configurations, we're talking about the system as a whole without really knowing exactly where the molecules are. In this example with the rooms, we're just talking about particular states. Messy is a particular state, clean is a particular state, but we're not talking about the number of configurations that our room could actually have. In fact, if this room is larger, this room actually could have more configurations.
Before we'll proceed, let me teach you first about the sign of entropy. Entropy increases when delta S is positive and the entropy decreases when the delta S is negative. Entropy increases too as one goes from a solid to a liquid, or more dramatically, a liquid to gas. So how can we calculate the change in entropy? The formula in getting the change in entropy is delta S reaction equals to summation of the standard entropy of the product minus the summation of the standard entropy of the reactants. Example problem. Find the change of entropy for the hydrolysis of urea. We can solve the problem with the help of the given following standard entropy values. We'll use the formula and substitute. For the product side, CO2 is 213.6 with 1 mole, plus NH3 is 192.3 with 2 mole, minus the reactants, CONH22 is 173.8 with 1 mole, plus water is 69.9 with 1 mole. Through this process, we got the change in entropy, which is 354.9 joules per Kelvin. The result is positive, therefore it is spontaneous, and if the result is negative, it is non-spontaneous.
When you clean your room, it doesn't stay here on its own unless you do work each day to keep things picked up. Your shoes find their way out of the closet to the side of your bed. The jewelry, coins, and the beauty products on your dresser get all jumbled up. Your laundry pile grows every time you try to decide which outfit to wear, and the bed cover are all scrambled. The chaos of the teenager's bedroom is a perfect example of entropy.
A campfire is an example of entropy. The solid wood burns and becomes ash, smoke, and gases, all of which are more disordered than the solid fuel.
Oh, so this is entropy, Dan?
Yes, that is entropy. Did you hear something about it?
Yes, Dan, a lot.
Very good, my dear. You're such a smart kid.
Thank you, Dad.
You're very welcome.
Audio Jungle.